Alright everybody, welcome back to Mr. Buckingham's Physics Solutions. So again, we're working with the kinematics problems, and we're going to go ahead and work on problem number 6. Now this problem presents us some unique challenges that we're going to try to work through here. So let's go ahead and dive in. A juvenile delinquent, hopefully that's none of you guys, throws a rock at a skylight and knows, having taken physics, that the glass will break only if the rock is traveling at least 15 meters per second. I'm going to underline that, on contact. If the skylight is 4 meters, so I'm going to underline that, above him, how fast must the rock be thrown? Alright, so this one presents us with some unique challenges, but we're going to start actually with writing down the information and then drawing a picture, just like always. Alright, so going back through the problem, we have a speed, that is that VF, our final velocity, must be at least 15 meters per second. Okay, and we have a distance, that is x, is equal to 4 meters. Alright, and that's the distance above him that this is. Alright guys, welcome back to Mr. Buckingham's Physics Problem Solutions. In this edition, we're going to be going over problem number 6 of our kinematics problems. Let's go ahead and read it. A juvenile delinquent, hopefully that's not you, throws a rock at a skylight and knows, having taken physics, that the glass will break only if the rock is traveling at least 15 meters per second, so we're going to underline that, on contact. If the skylight is 4 meters, underline, above him, how fast, we're going to circle that because that's our question, must the rock be thrown? Alright, a couple of things that we're going to go ahead and start this with. Number one is that we're going to draw a picture, and that is of our student here throwing a rock up at the window. The first thing that we need to know is that the window is 4 meters above him, okay? So our height here is 4 meters. The second thing to know is that when the rock reaches the window, its initial speed, or its final speed, once it hits the window, has to be at least 15 meters per second, alright? What we're trying to do is calculate how fast you have to throw it so that by the time it reaches the window, it's going 15 meters per second. So we're going to go ahead and copy down some of the things we know. We know our final velocity here is 15 meters per second. We know the change in height is 4 meters. And we know that the acceleration due to gravity always is 9.8 meters per second. Now, in this case, we're actually going to give this a negative, and we want to get in this habit of considering gravity to be a negative 9.8 meters per second squared. That is to say that up is in the positive direction and down is in the negative. Since acceleration due to gravity is always pointing down, we're going to consider that to be a negative acceleration this time. Again, remember that the positives and negatives here only have to do with the direction in which we're going. Since we're thinking of an object starting out fast and slowing down, okay, acceleration should be negative in this case, going the opposite of the initial velocity. We're going to go ahead and pull out this equation to solve this problem and write it down. Right? One of the nice things about this equation is it avoids using time while we can still solve using things like acceleration and the distance that it's gone. This also requires us to know a final velocity and an initial velocity. Right? In this case, we're solving for our initial velocity, right? This is what we want to solve for, so I'm going to do a little math. I'm going to move the 2a delta x from one side over to the other by subtracting it from both sides. Now we have something that looks like this. Okay, we've got v, that's our final velocity, squared, minus 2a delta x is equal to our initial velocity squared. Alright, we haven't done much. All we did was move this 2ax over to the left side of the equals. Now what we're going to do is start plugging in some numbers. Remember, at the end of the day, we're trying to solve for v naught. Here, I plug in my initial speed, or my final speed. Remember, this is final speed when we hit the window of 15 meters per second. Add all of that squared. Minus 2 times the acceleration due to gravity, that's negative 9.8 meters per second, squared, times 4, right? 4 being the delta x, that is the change in height from way the person threw it till when it hits the window, is all equal to V naught squared. Alright, we can solve this out. We're going to do our 2 times 4 times 9.8, okay? That gets us 39.2. 15 squared is 225. So I'm going to add those two together, and we get 264.2 is equal to V naught squared. To get rid of this squared, we're going to take the square root of both numbers. We'll end up with our initial speed has to be at least 16.2 meters per second in order to break the window. Right? Going back to our initial problem, remember what this means. This initial speed here, right? This is all about how fast does it need to go so that it breaks through our window, okay, when it actually hits here, right? We want to see how can we make it actually break through the window. How fast does it need to be going? Originally 16.2 meters per second. One other way to think about this is that it's the 16.2 meters per second is our initial speed. In the time that it goes from our hand up to the window, it slows down to 15 meters per second because of the acceleration due to gravity. Right? So there's a couple of different ways that you can think about this problem, but at the end of the day, what we're trying to do, again, is isolate the variable that we want. Here it was V naught. We tried to get it all by itself on one side of the equals, and then plug in all the numbers. Right? Hopefully this helps you quite a bit. If not, make sure to come in and talk to me. Once again, I hope you enjoy the rest of your time and that this is helping you out.